In this video, we're going to cover Chapter 5, Continuous Random Variables. Let's begin with an introduction. So let's talk about the properties of what's called a continuous probability distribution function. So in the last few chapters, we talked about discrete random variables and discrete probability distribution functions. This time we're going to move into the realm of continuous. So the graph of continuous probability distribution functions are curves. So those are like what you would have graphed in your algebra courses, and we can do in Desmos. So these are curves with area underneath them. As we're discrete probability distributions are more like dots. They're jumps, and we measure those in enumeration. As we're with continuous random variables, we consider them kind of on a spectrum. They're continuous, they're measurable. So the curve is actually called the probability density function. It's a usually abbreviated PDF, and we use the symbol f of x to represent the curve. So this is going to correspond to some graph that we can look at, and we often want to draw the graph so we have a visual representation. Now, beyond the few basic examples I'm going to show you in this chapter, which is going to be the uniform distribution, when we move into more advanced, we will have to solely rely on technology just due to the complexity of the math. So what we're really looking at when we're talking about probabilities for PDFs, we're really looking at what's the area under the curve. So what's called the area under the curve. And this is where it can get quite complicated, because with complicated functions, you have complicated curves, and you would have complicated math necessary to find their areas. So when we add up, when we accumulate area, we add up that area, we call that a cumulative distribution function, often called a CDF. So there's two functions, PDF, probability distribution, CDF, cumulative. So cumulative adds up everything from the start up to a particular point. So the cumulative distribution function is used to evaluate probabilities as areas. Again, we use technology heavily to find this. For continuous functions, outcomes are measured and not counted. So measurable things are like height, weight, blood sugar level is a measurable thing. You don't count your blood sugar level. Counting is like when we had the number of shoes or the number of people in a classroom, number of books you've bought. So that tends to be more discrete. And then here we're talking about measurable things, continuous variables. So the entire area under a PDF has to equal 1. In order to be a valid probability distribution function, we know that it has to add up to 1. Here, when we add up all of the area under the curve, we have to equal 1. And the probability is found for intervals rather than for individual values. And this is different than what we had for discrete variables. We did have probabilities for specific values in discrete variables. Here with continuous functions, we do not. And I'm going to summarize that more on this page. So this is how we write a probability statement. We say the probability that C is less than X is less than D. And that is the probability that the random variable we're looking for varies between the values of C and D. And so the probability that C is less than X is less than D is the area under that curve that's bounded between the curve and the X-axis. And it's going to be to the right of C, but to the left of D. So it's kind of trapped in between C and D. Now this next paragraph is where and that's kind of the same as what we did for discrete. We added up all the things between like 1, 2, 3, and 4, or 5, 6, 7, and 8, so things like that. This is where continuous differs in this next paragraph. Notice it says the probability X equals C is 0. And so what that means is the probability distribution function for continuous variables do not take on individual values, because a line, if you just drew a straight line from the curve down to the x-axis, a straight line has no area. So that 0 area means that specific values have have 0 probability. We would essentially say that they're guaranteed to not happen. And a good example I have of this is a little game or a little demonstration I would play if we were in person or if this was live, but I can kind of do it here. And I want you to take a minute. Now I want you to pick a number between 1 and 10. Any number between 1 and 10. Pick it. Okay? Did you pick 6.28? The likelihood that you pick 6.28, or the probability, sorry, that you pick 6.28 is 0. Because that is one specific number in the infinite number of numbers that is between 1 and 10. So even between 1 and 2, there is an infinite number of numbers. Like there's 1.1, 1.2, and even between those, there's an infinite number of numbers. So the likelihood, or the probability that you would pick that exact number that I pick, 6.28, is, the probability is 0 in this case. Now, you know, there could be a little bit of argument that if you know me and you know that there's a particular significance to 6.28, which is actually the first 3 digits of 2 pi, then you might be able to guess 6.28. But again, randomly, the probability is 0. And then the last paragraph is also interesting, but applies that idea that specific values take on 0 probability, and that's that if you write the inequality statement with strict inequality, so C is less than X is less than D, versus the inclusive inequality, C is less than or equal to X is less than or equal to D, that doesn't change the probability. Including the endpoints doesn't add any probability, because probability at exactly 1 point is 0. So whether you add C in or leave C out, in a continuous PDF, that's not going to change anything. Again, that's a divergence from the discrete case where equals was possible and we did have values. So now we have it's a little more powerful, but also a little, I guess, could be a little more confusing in some cases. But just remember that for continuous random variables, we do not have exact values for probability because it's no area. So again, the big picture here for continuous probability functions is that probability equals area. So if you have area, you have probability. If you have no area, you have no probability. So let's look at this example. We've got this function f of x equals 1 over 20 for 0 is less than or equal to x is less than or equal to 20, where x is just any real number. So I could pick, 2 pi, 6.28. I could pick pi, 3.14, anything in between there. So the graph of f of x is equal to 1 over 20. That should be 1 over 20, sorry, that's a typo. And that's a horizontal line. I've got it graphed over there on the right. It is restricted from 1 to 20, and we'll talk about why that is in just a second. And it is between x equals 0 and x equals 20 inclusively. So we can be at 0 or we can be at 20. So thinking about this as an area, let's think about, does this equal 1? So this is a rectangle. Rectangles have area base times height. And so the base here is 20 and the height is 1 over 20. So if we multiply that, that's 20 over 20, that's 1. So this gives us an area of 1. This is a valid probability density function. So let's go ahead now that we know that this is a true PDF and answer these questions. So let's find the probability that 2.3 is less than or equal to x is less than or equal to 12.7. So again, if we were to kind of draw a line here, let me see if I can get a pen in here. So let's say we drew a line about right here. So that would be at about 2.13, and then maybe about right here, about 12.7. Then what we're looking at really is kind of this area right in here. And so this distance, this base distance, is going to be 12.7 minus 2.3. And then this height is constant at 1 over 20. So 12.7 minus 2.3 times 1 over 20 is going to give us 10.4 over 20, which is 0.52. And that's a typo. So that gives us that area. So we would say that the probability is 0.52. We could also say that there's a 52% chance that you would select a number. If you were thinking about this as randomly, you have the equal likelihood of picking any of those numbers, that there's a 52% chance that you would pick a number in that range if you were just randomly picking numbers. So part 2 says, is this any different? Well, the answer is no. There's no difference in including the endpoints because the probability at x equals 2.3 is 0, and the probability that x equals 12.7 is 0. So making this probability exclusive rather than inclusive does not change the probability in this case. So I want you to take a moment, pause the video, and see if you can answer this question by yourself. All right, hopefully you took the time to pause and pondered upon that. So let's look at the solution. So here's the graph, f of x equals 1 over 8, and then x equals 8. And so the probability that it's between 2.5 and 7.5 is, again, the base. If I drew, let me get my pen out here again. So 7.5 is going to be pretty close to the end. So that was not straight. And about 2.5 is going to be somewhere around maybe like, I don't know, right there. And so we're looking at kind of that area. So this base right here is going to be 7.5 minus 2.5. And then the height is constant at 1.8. So that gives us, if we multiply those together, 0.625. So that is going to be the probability. And that's really the end of that particular section, that kind of introduction to probability distribution functions. So let's keep moving right along into 5.2 and talk about the uniform distribution. So this is going to be our first example of an actual CDF distribution. So the uniform distribution is a continuous probability distribution, and it is concerned where all possible events from our sample space are all equally likely. So an example of this is like you roll a die. All of the numbers, 1, 2, 3, 4, 5, and 6, are all equally likely. Now that is technically discrete because you can only get 1, 2, 3, 4, 5, or 6. So that is the discrete uniform distribution. This is continuous. So anything in between the numbers is equally likely. So when working out problems, I think that it is highly important that you draw the graph, but you also have to be careful to note if the data is inclusive or exclusive of the endpoints. We know that probability at the endpoints doesn't add to the probability, but it is important to make sure that you understand the problem. And then the other thing I want to point out on this slide is that we have this notation here. So this notation here is important for us. So I just want to highlight it. And so this says that the random variable, in this case x is continuous, is coming from the uniform distribution between the values of a and b. All right, so going forward, we're going to see a lot of this type of notation in the course because we're needing to signify which PDF or what type of distribution this information is coming from. So this is the uniform distribution. So it looks like this. This is called, we typically call it a piecewise defined function with this curly brace. And then we have these cases. So the first case is that if a is less than or equal to x is less than or equal to b, which is our values that we want, our smallest and our largest, then it takes on the value of 1 over b minus a. If it's outside of that region, then the distribution takes on the value of 0, which means that you can't be any of those values. You have no likelihood or probability of being those values. For the uniform distribution, we have these formulas for the mean. So the mean is a plus b over 2. This should seem kind of obvious. It's just the average of the highest divided by the lowest, since everything is equally likely. The one that isn't obvious and would take a little bit of complex math to solve it, but we're just going to use it, we're just going to consider it a formula, is the standard deviation of the uniform distribution. So again, that's the sigma symbol. It's the square root of parentheses b minus a quantity squared all over 12. So b minus a is the only thing that changes in this formula. 12 is a constant, and then we take the square root of it. All right, so mean, mu, is the average of the max and min, and sigma is the kind of the range. That's b minus a is the range, max minus min. We square that, divide it by 12, and then take the square root. And again, 12 is a constant. It doesn't change. So in the textbook, there's a table, and it's also loaded into your Chapter 5 mini-tab worksheet if you're following along. We have this example where we collected 55, so we sampled 55 children, and this nurse measured how many seconds the child at 8 weeks old smiled at the mother. So we assume that smiling time in seconds is a uniform distribution where they smiled 0 seconds all the way up to possible 23 seconds. And so we're going to go through these 6 questions. We're going to create an empirical distribution histogram with a bin size of 0.2. I'm actually going to create a little bit larger bin size. It'll help show kind of the uniformity of it. Otherwise, it doesn't look really uniform. Then we're going to calculate the empirical mean. So this is the same thing as the sample mean. And then the empirical standard deviation. Again, sample standard deviation. Theoretical mean, we're going to use a formula. Theoretical standard deviation, formula. And then we're going to compare those values. So let's start with the empirical distribution histogram. And I'll do it with the 0.2, and then I'll show you that if we increase it, it starts to look a little more uniform. So I'm going to move over here. I've got Minitab and Desmos open. We'll need both of those. And I'm in that Chapter 5 Minitab worksheet. You'll need to download that from the LMS if you're going to follow along with me. So you'll see this first tab is Smile in Seconds. So we're going to create a graph with Graph Builder. I'm going to reset because I had already done this before. So smile, we grab, drag, and drop into the variables section, and then we've got this histogram option that already pops up. Now for PDFs, we need to make sure this is percents. Okay, so for PDFs, you need to make sure that the scale on the y-axis is a percent. So I'm going to click Create. So you can see here a few things going wrong with this. First of all, these are at midpoints. That's not typically how we like it. And it doesn't really look uniform. I don't think this data in general looks very uniform, but we're going to use it because it's the book example. So I clicked on the graph. I'm going to click on this chevron, which is the drop-down arrow, and I'm going to go to Graph Options. So remember, under Scales is where we have the ability to change it to cut points so that it goes 0 to whatever. And then the book wants us to use 0.2. So let's start with that. And so you can see from 0.2, this is pretty good. Let's close this for a second. So other than these anomalies, these peaks right here, everything kind of looks to be about the same. You know, this is 1.818%. So we're talking about like these values. So between 0.06 and 0.08 is taking on a value of 0.18. So you can kind of see it's kind of uniform except for these peaks. It's not great. Again, it's the best we're going to do with quote unquote real data. It's kind of 30 intervals. You can kind of see you got these peaks going on. If we just let it choose, you can kind of see, but again, it doesn't have it looks more normal. But the book is arguing that this is uniform, so we're going to stick with that uniform argument. So, but this is kind of the graph that I chose. Again, we're talking about uniformity. We're kind of talking about things that are centered around here-ish, okay, for the outcomes. So the empirical mean is just the mean that we get from Minitab. So to get that, we would go to Stat, Basic Statistics, and then Display Descriptive Statistics. So I've already loaded in smiles in seconds, but you might need to click it and select to get that variable in there. Click Statistics. I'm going to click None. I know we're going to need the mean, and we're going to need the standard deviation. That's really all we need. I'll go ahead and do max and min, just because it is uniform. That's usually our close estimate of A and B. And then N total is the number. We really want to get used to using N total. It'll come in very handy later and in the rest of the semester. So everything else we don't really need, but I'm going to go ahead and click OK. So now we have the mean and we have the standard deviation for our sample, and there are 55, of course. We already said that. So we've got our data loaded in. We can see the minimum was 0.7 and the maximum was 22.8. So that's why that they claimed that it was uniformly distributed from 0. That would be the lowest. The baby didn't smile at all, or no seconds. And then the maximum is 22.8, so we'll go ahead and round that up to 23 seconds. So that empirical mean was that 11.627. Empirical standard deviation, just again that number, I hate to keep scrolling back and forth, but that 6.08 just comes straight again from Minitab, from those descriptive statistics. Now the theoretical mean we're going to calculate from the formula. So this was mu equals b plus a, or a plus b divided by 2. And so went ahead and worked that out for us here. So 0 plus 23 divided by 2 is 11.5. So what this means is theoretically we would expect on average a child to smile for about an 8-week-old child, baby, or 8-week-old baby to smile for about 11.5 seconds. And the theoretical standard deviation, again, that is an equation or a formula, and that's going to be sigma equals the square root of quote or parentheses b minus a quantity squared all over 12. And so we get this. And I would just put this into Desmos, make sure the 12 is in the radical, and then you get 6.640. And so that's the theoretical standard deviation. So how do these compare with the empirical versus the theoretical? So I have them all here on this slide. We can see that the means are fairly close. They're only different by, kind of about less than 0.1 difference. I guess that is a 0.1 difference, a little more than a 0.1 difference. The standard deviations are higher, like they're differing by about 0.5 something there. But that's still half of a second. When we're talking about mean and standard deviation, they're the same units of measure. So we're talking about half a second and, 0.1 something of a second difference. So they're fairly close. They're not exact, which we would expect. Empirical is not always going to match the theoretical, but they're fairly close. So here's our first try it. I want you to take a moment and stop. Now I'm going to clarify something. When it says calculate the empirical mean and standard deviation, that's already given to you. You don't actually have to calculate anything. The sample mean and the sample standard deviation are actually given in this problem. I just copied and pasted the instructions from the previous problem, which is why they appear like that. So take a moment, pause the video, see if you can answer these 5 questions, and then we'll go over the answers. All right, so hopefully you took the time to pause the video, but now let's go through. So what are A and B? So it says that it's uniformly distributed where it is including 0 and 14. So that means A is going to be 0 and B is going to be 14, and everything in there in between is going to be equally likely. So writing the distribution in proper notation requires that after we've identified A, which is 0, and B, which is 14, we need to do the f of x equals 1 over b minus a. So that's going to be 14 minus 0. That's just going to be 1 over 14. So it's going to look like this. It's going to be 1 over 14, and it's going to range from 0 to 14. And these are including, so they are inclusive, so it's equals on these in this case. So this is what the distribution would look like in proper notation. We could also say that x, another way to put it is that x comes from u a, B. I'm sorry, writing with a mouse is not fun. Let me see if I can get my mouse here better. So where so it would come from 0, 14. So that would be also how we could write the distribution. So this is the PDF and this is the distribution notation. So we kind of want to have both of those. So again, empirical mean was given in the problem, that's 7.9, and then the theoretical mean is the average between the min and the max. So the minimum here was 0 and 14, so 0 plus 14 is 14 divided by 2 is 7. So a little further off than our last example. And then the empirical and theoretical standard deviation, the empirical standard deviation is given, it's 4.33, and then to find the standard deviation, again, you would plug it into that formula, which is equal to the square root of b minus a quantity squared all over 12. And that should give you the 4.041. And how do these compare? Well, again, they're not as close as the smiling baby example, but they're fairly close. Like we're off by 0.2 something there. We were off by 0.9 for the mean. So close, but again, we expect the empirical to not match the theoretical. So going back to the baby example, what is the probability that a randomly chosen 8-week-old baby smiles between 2 and 18 seconds? So to solve this is problem A in the guided notes or in the textbook. To solve this, we're going to need the PDF. So in this case, I just shorthanded the PDF. So technically it should have been with a bracket where this is between 0 is less than or equal to x is less than or equal to 23. And then 0 otherwise. So that would be that. Again, I'll try to draw a quick sketch here. So we've got here, this is 1 out of 23 in this case. And so between 2 and 18, so kind of, it comes all the way out to 23. So 18, 2, we're looking for this area in here, which models exactly what we did last time. So the area is going to be the difference from 18 to 2, and then multiplied by the height of the distribution, which is 1 out of 23. So that ends up giving 16 out of 23, which is about or equals to 69.57. I think that's rounded to 4 decimal places. It's not an exact there. So that's going to be the probability. Again, we're finding the area under the curve here. So find the probability that a random 8-week-old baby smiles more than 12 seconds, knowing that the baby smiles more than 8 seconds. So knowing we can write as the same thing as given. All right. So when we say knowing, we're kind of talking about like we're given information. So this would look like the probability that x is greater than 8 seconds given that it is, I'm sorry, I got those backwards. 1 second. Yeah, so smiles more than 12 seconds knowing the baby smiles more than 8 seconds. So it's more than 12 seconds knowing that the baby smiles more than 8 seconds. So this one's a little more complicated. Let's take a look at the solution. So in this case, it is a conditional probability. So if we know that the baby smiles more than 8 seconds, then we can kind of think of the new PDF as being 1 over 23 minus 8. So just to give us a picture here, our original is 1 out of 23. But now we know that we're only looking at babies that were smiling more than 8 seconds in this case. So, and then this is all the way out to 23. So we are only concerned with things in this distance, which is making this base kind of 15. I'll explain this in a different way in just a minute, but just if this makes sense to you, let's talk about this. So the fact that it's greater than 12 given that it was greater than 8, by being greater than 8, it restricts us to only the last 15 seconds, starting from 8 going out to 23, and then the distance from 23 out to 12, because greater than, or x is greater than 12 would be from 12 seconds all the way out to 23 seconds. That's going to be 23 minus 12 out of, this was the kind of the modified probability with that given information gives us this. Let's look at it in a different way. Let me get just a blank white screen. So we know that f of x is, again, 1 out of 23 or 0. And then you've got the conditions. So the probability that x is greater than 12 given that x is greater than 8, using the and law that we talked about a long time ago. Remember, given A given B is the probability of A and B. So that would be that x is greater than 12 and x is greater than 8 divided by the probability that x is greater than 8. So let's think about each of these. So the probability that x is greater than 12 and greater than 8, well, think about a number line. Let's say here's 8, here's 12. In order to be greater than 8 and 12, you have to just be greater than 12, right? Because if you're like 9, that's greater than 8, but it's not greater than 12. So to be greater than 8 and 12, you have to be greater than the largest value there. So thinking about that, that's just the same thing as the probability that x is greater than 12 divided by the probability that x is greater than 8. Now from there, we don't have any conditionals. We've kind of gotten rid of the conditionals using the multiplication rule. So now x is greater than 12 is just going to be what we normally would say is 23 minus 12 times 1 over 23 all over. And then that's greater than 8 is going to be 23 minus 8 times 1 over 23. And so what ends up happening is you've got these 1 over 23s on the top and bottom. They end up canceling. So you end up with 23 minus 12 over 23 minus 8. 23, just to write that next step, 23 minus 12 over 23 minus 8. So that's going to give you your 11 on top and 8 minus, or 23 minus 8 on the bottom of 15. And so that should match. We'll go back to unwipe the screen. 11 out of 15. So, oh, it erased all my, sorry. So you can pause the video and go back to that whiteboard and look at that again. But you can see that there's two ways to logic through this. Whichever one you're more comfortable with, just pick that one and go with it. My only word of caution is that make sure that you look carefully at which way your inequalities are going. So with that, again, we've come to a point where I would like for you to pause the video and kind of try this yourself and see if you can master that information. All right, so hopefully you took the time to pause the video. So let's go through the answers. So A and B, A is the lower and B is the larger. So 447 is the smallest up to 521. We would say that x comes from u, AB, and then if we would write the distribution here, f of x equals, and it would be 1 over, and then we would do 521 minus 447, so that's going to give us 74. And then it's going to be from 447 is less than or equal to x is less than or equal to 521. And we do use equals because it does say inclusive of those. So to find the mean and the standard deviation, again, a plus b divided by 2 would be the mean. So we're just finding the average of the smallest and the largest. And then the standard deviation is going to be the range squared all over 2 and then taking the square root of that value. So got quite a large standard deviation comparatively. I guess we're talking about the number of hours a baseball game season. So, I mean, there's a lot of hours in a baseball game, cumulative in a baseball game over an entire season. So, kind of makes sense. And then what's the probability that the duration of a game for a team in a single season is between 480 and 500? Again, there's not conditionals here, so it's just the straight up area. So 500 minus 480 divided by 1 out of 74, and we get 0.2703. So I'm going to stop the video here and give you time to kind of think of this as a homework problem to put it all together, and then we will talk about this, or I will post the answers if you see me in person.